welcome you all back for the lecture series of radiation heat transfer. So far we have discussed what is radiation and the basic laws which governs the radiation, and then we have gone for the radiation shield concept. Now we are going to see how the radiation happens, or how the radiation heat transfer happens between two surfaces and three surfaces, right? Before getting into that problem solving method, we are going to see some basic definitions, which is irradiation and radiosity. First one, irradiation. First one, irradiation. Now consider an object in which the solar radiation is fall on that object. Now irradiation is nothing but the total amount of solar radiation which is incident upon a body is called as irradiation. Okay. So now the total radiation incident upon a surface, incident upon a surface per unit time per unit area. Okay, this is called irradiation. It is expressed in watt per meter squared. Then the second thing you have to know what is radiosity. So now in an object there are a lot of radiation falls on an object which is called as irradiation. Now the object which absorbs all the energy which is incident upon that and emits some of the energy which is absorbed by that, right? So that emission power is known as, that emissivity is known as radiosity. It can be written as, it is used to indicate the total radiation leaving from the surface. Leaving from the surface per unit time per unit area. It is also expressed in watt per meter squared. Okay. Now this radiosity consists of two components. One is the radiation which is emitted by the surface, and the another one is the radiation which is reflected by the surface. Okay. So the first component is reflected by the surface. Reflected by the surface, which is equal to the reflectivity. You know the reflectivity value rho, which is total energy incident on that in the denominator, and in the numerator which is total amount of energy transmitted, that is called as rho into G. G is nothing but your irradiation amount, right? So here irradiation is known as capital G and the radiosity is known as capital J. Okay. So rho into G, which gives the reflected amount of heat, reflected amount of energy from the surface. Now the second component is emitted by the surface. Emitted by the surface, which is known as epsilon into EB. EB is known as the emissive power of the black body. That is a maximum amount of energy a body which can emit, right? So epsilon is the emissivity of the grey body. So epsilon into EB becomes the emitted by the surface. So now the total amount of radiosity, J equal to rho into G plus epsilon into EB. So now consider an opaque surface. For opaque surface, the transmissivity value tau equal to 0. Okay. So if tau equal to 0, you know that alpha plus rho plus tau equal to 1. Now since it is 0, alpha plus rho equal to 1. You can rewrite this equation as rho equal to 1 minus alpha. Now just substitute this value in this equation. So you will get J equal to 1 minus alpha into G plus epsilon into EB. From Kirchhoff law, you know that alpha equal to epsilon. From Kirchhoff's law, you know that alpha equal to epsilon. Okay. Now just substitute this in this equation, we'll get J equal to 1 minus epsilon into G plus epsilon into EB. Now I am going to derive an equation for the value of G from this equation. Now 1 minus epsilon into G equal to J minus epsilon into EB. Now G equal to J minus epsilon EB divided by 1 minus epsilon. This is the formula for G value. Now you know that the net energy leaving the surface, net energy leaving the surface is equal to Q122, the heat amount of heat transfer from surface number 1 to surface number 2 divided by per unit area, which is equal to J minus G. Now I am going to substitute this G value here. Okay, Q12 divided by A equal to J minus epsilon EB divided by 1 minus epsilon. Okay. Now if you take 1 minus epsilon as common term and simplify this equation, you will get epsilon into EB minus J divided by 1 minus epsilon. This can be rewritten as EB minus J divided by 1 minus epsilon divided by epsilon. Now this is known as Q12 divided by A. Okay. Now this is represented as the electrical circuit, right? So like this, it can be represented like this. So this is EB and this is J, and the heat, this one is called as 1 minus epsilon divided by epsilon. This is known as the resistance. Okay, the term 1 minus epsilon divided by epsilon is known as surface resistance. Surface. Now the second thing, very important thing, which is known as shape factor or view factor. First one, shape factor or view factor. Now consider two objects. This is object number 1 and this is object number 2. The object number 1 is at a temperature T1 and object number 2 is at a temperature T2. Consider that T1 is greater than T2. So the object number 1 is always emitting radiation in all directions. Like this, in all directions it will emit radiations, right? So the total amount of radiation emitted by the object number 1 is considered as 100 kilowatts. Now if this object emits radiation in this direction, which are going to absorbed by the object number 2. So that amount of radiation which is received by the object 2 will be 20 kilowatt only, right? So 100 kilowatt energy is emitted by the object number 1 and only 20 kilowatt energy is absorbed by the object number 2 because of the shape factor, because of its dimension or because of its shape, right? So this value is known as shape factor. Now 100 into 0.2 gives 20. This 0.2 is the shape factor F. This is known as F. Now the definition for the shape factor is, it is defined as the fraction of radiative energy that is diffused from one surface and strikes on other surface directly without any intervening reflections, right? So it is also called as shape factor, view factor, configuration factor or angle factor. Now the concept of shape factor becomes when there are two surfaces comes into play, right? So now we are going to see what is how the radiation heat exchange between two gray bodies. So that will be the heading, radiation heat exchange between two gray bodies. Okay, consider two bodies radiating each other. This is object number 1 or body number 1, this is object number 2 or body number 2. Now from the first surface, there is number 1 surface, it is emitting radiation in all directions. I am considering only in this direction. The surface, the energy leaving from the surface per unit area is called as J. Since it is object number 1, it is called as J1. Now J1 is per unit area, per unit area. In order to consider all the radiation emitting from the surface 1, I am multiplying the area A1. So the energy leaving from the surface 1 is called as J1 into A1. Similarly, the energy leaving from the surface is known as J2 into A2 from the second surface, right? This is what I am going to write now. The heat radiated by first body and received by second body. Okay, the heat radiated by the first body is known as, J1 into A1. Now the second body receives that energy as per the shape factor 1, 2. So the heat radiated by the first body and which is with the amount of energy absorbed by the second body is known as J1 A1 F12. Similarly, heat radiated by second body and received by first body will be, that J2 into A2, the shape factor F21, right? So now the total amount of heat exchange Q12 is equal to J1 A1 F12 minus J2 A2 F21. Now later we will discuss some of the rules. Now I am going to use one of that rule now, which is reciprocity relation. The reciprocity relation is nothing but A1 F12 equal to A2 F21. So I can substitute A2 F21 as A1 F12. So I am taking A1 F12 as common term in bracket J1 minus J2, right? So now Q12 is equal to J1 minus J2. I am just rewriting this equation, 1 divided by A1 F12. Now I can represent this in electrical circuit like this. Okay, this is J1, this is J2, and this is the resistance A1 F12. So now 1 divided by A1 F12 is known as space resistance. Okay, now you know the formulas for space resistance and surface resistance. Now I am going to consider two surfaces like this. This is one wall of a room. Maybe this is the space in the room and this is another wall. Now from here to here, for the heat exchange there will be some resistance. This resistance is called as surface resistance. Similarly, from this point to this point there will be surface resistance, and from this point to this point there will be space resistance, right? This is the net heat energy radiation between two surfaces. This can be represented by a electrical circuit. Here there will be one resistance, here will be second resistance, here there will be third resistance. So I am going to consider three resistance, one second resistance, and this is my third resistance, right? So here it will be EB1, and here in the junction it is J1, and here it is J2, and here it is EB2, right? So here it is surface resistance, right? So this is surface resistance, this is space resistance, this is surface resistance. You know the formula for surface resistance, which is 1 minus epsilon 1 divided by A1 epsilon 1. Similarly, here also surface resistance, but it is in the surface number 2. This is surface number 1, this is surface number 2. So I am considering 1 minus epsilon 2 divided by A2 epsilon 2. Here it is space resistance. You know the formula, 1 divided by A1 F12, right? This is the electrical circuit for two surfaces. Now from this surface you can calculate Q12. Q12 is EB1 minus EB2. This first term and the last term divided by, you can sum up all the resistance in denominator. 1 minus epsilon 1 divided by A1 epsilon 1 plus 1 divided by A1 F12 plus 1 minus epsilon 2 divided by A2 epsilon 2. Okay, for black surfaces, for a black body, the value of epsilon equal to 0, sorry 1. So epsilon 1 equal to epsilon 2 equal to 1 for black surfaces. If you substitute epsilon 1 and epsilon 2 here, 1 minus 1, so this term will be 0, and 1 minus 1, this term will be 0. Again, the total energy leaving the surface will be EB1 minus EB2 into A1 F12. This EB, you know that from Stephen Boltzmann law, sigma T power 4. So now I am substituting sigma T1 power 4 minus sigma T2 power 4 into A1 F12. This sigma can be written common, and sigma into T1 power 4 minus T2 power 4 into A1 F12. This is the final equation for heat transfer between two surfaces, right? So this is nothing but the evaluation of Stephen Boltzmann law. Okay, thank you all.